Okay, so I'm going to talk about the 1976 summer heatwave and drought that occurred in the UK and, well, northwest Europe, but particularly affected the UK. And I've looked at trying to evaluate how the risk of this event has changed since the 1970s, between the 1970s and the present day, due to climate change. Or is it not getting right? Oh, there we go. Okay, so just a bit of background about the event. So in the summer of 1976, Northwest Europe and particularly the southeast of England experienced an extreme heatwave and drought. And so the drought occurred at the end of the dry 16-month period on record for the UK. So this meant that kind of going into the summer heatwave, the groundwater and reservoir levels, general water supply levels were very low already. So this obviously had some significant impacts on public water supply and water for agriculture and industry. So in some areas, they turned off the public water supply either completely. So the first picture here is old ladies having to go to standpipes in the street. So they turned off the supplies to houses and people had to fill up buckets from these pipes in the street. In some areas, they kind of limited the water supply in for specific parts of the day. And there were obviously limits on water use for agriculture and industry, which had kind of quite serious implications. So the third picture here is the River Thames, and it's showing some boats which were completely grounded because the river level was so low. So when I started this work, this was the hottest summer on record for central England. But then there was summer 2018, which was actually slightly hotter. But the significance of the 1976 event was the combination of the impacts of the very hot summer and also the prolonged dry period, which caused these serious impacts on the water supply. And it's particularly interesting as an event because the water industry considers it as a sort of benchmark extreme drought event. And since, I mean, it did occur quite a long time ago now, but because it occurred within living memory for many people, particularly people in kind of high up positions in the water industry, there's a kind of potential implicit assumption that the risk of the event might not have changed. But obviously, as we know that in the last 50 years, the climate has changed. So these are figures from Kendon et al. 2020. So this is for the UK. So it's showing the top. The top ones are for the UK as a whole, and then it's looking at individual regions. So England, Wales, Scotland, and Northern Ireland of regions of the UK. And you can see, so the first one is the temperature anomaly, and you can see that since the 1970s, there's been a considerable increase in the temperature in the UK as a whole and in England. And similarly for the precipitation, overall, there's been a slight increase in overall precipitation. So the UK climate has become generally warmer and wetter since the 1970s. So given this changing climate, the aim is to evaluate how whether the risk of the 1976 type heatwave and drought event has increased since the 1970s. So the methodology I've used is using the principles of event attribution to assess the probability of the 1976 event in the 1970s and in the present day climate. So I've used two different methods based on climate models. The first is using coupled climate models. So I used existing CMIP5 data for the 1970s and the recent decade. I used 15 different CMIP5 models and then the 10 years in each of the decades, so that's 150 years of data for each period. And then the second method is using atmosphere-only simulations, which I ran using HAJM 3A. So this is the Met Office kind of climate model run with prescribed sea surface temperatures. So I ran 150 years of simulations with 1976 sea surface temperatures and greenhouse gases and aerosols and things. And then I ran a second set of the same, but with the SSTs perturbed to the recent decade climate. So adding on the kind of the warming signal, and also using corresponding recent greenhouse gas concentrations. So just to kind of give an overview of the event of what happened. So this is 1975 to 6. This is each month looking at the surface temperature anomalies and the contours of the mean sea level pressure anomalies in observations. And so you can see that there's for basically, apart from May, all the rest of the month there was a high pressure anomaly over most of Europe and particularly over the UK. And in the winter, so December, January, February, the anomalies in the UK and Western Europe were kind of warm anomalies, and then spring was kind of more average, and then the summer you can see the very strong positive temperature anomalies, particularly in June. So this time series is showing the surface temperatures in the England and Wales region, which is the box that's shown in the maps, the small box over England and Wales. So here the red is showing 1975-6 temperatures for each month, and then the grey lines are each of the years in the 50-year observation series, and then the black is the mean. So you can see the winter was kind of warmer than average, spring was fairly average, and then the summer was exceptionally hot, particularly in June. Similarly for precipitation, you can see that in all these 9 months, the precipitation was very low in Northwest Europe. So it's lower than average, apart from May, which was kind of average. And so, yeah, so again, you can see the top plot is the monthly precipitation for England and Wales region, and you can see in each of the months the 1975-6 precipitation was very low, and particularly the summer was exceptionally low. And then the bottom plot is the accumulated precipitation. So you can see that by the end of this 9-month period, the accumulated precipitation is kind of just over half what it would normally be for that period. But actually, given that we know that we were going into the winter 75-6 with already kind of having experienced several months of low rainfall, it was kind of even more extreme than that. So the first kind of stage in terms of the looking at the event risk is to define what the event is. So I'm focusing on the England and Wales region, and I kind of identified the 3 key factors that contributed to the drought in summer 1976. So these were the dry winter-spring periods leading up to the summer. So this is important for kind of groundwater and reservoir recharge. The dry summer, which was important for water demand, and then the hot summer, which is important for water demand and the sort of overall impacts of the event. And I first considered these 3 components separately. And then if there's time, I'll go on a bit to show looking at sort of joint probabilities of these 3 factors. And so I've defined the event based on the 1975-6 observed temperature and precipitation anomalies. as the thresholds to define what we mean by extreme years in the models. So these figures are showing, so the blue is the observations, the pink is the HAGEM, so that's the atmosphere-only simulations, and then the yellow is CMEP5, which is the couple simulations. The black dashed vertical lines are showing the observed anomalies in 1975-6. So this is what I've used as a threshold to define the extreme events. So you can see from these that the models are doing a good job of getting the kind of overall distributions of temperature and precipitation, and matches the observations well. And the other thing to note is that in both the model sets, there is at least one extreme event for each quantity. So this is the 1970s climate. So for the precipitation, we're looking at values below the threshold, and then for temperature, we're looking at values above the threshold. So then moving on to looking at how the event probability has changed between the 1970s and the recent decade. So this is looking at the temperature first. So the purple here are the 1970s climate, and then the orange is the recent decade climate. And you can see that there's a very clear shift, which is what we'd expect really, to warmer temperatures. So using this data, I calculated the return periods in the 1970s and the 2010s, the recent decade. So based on the coupled simulations, the return period in the 1970s of such a hot summer was 50 years, and this has decreased to 6 years. And then based on the atmosphere-only simulations, this has gone from 150 years to 8 years. And so these result in risk ratios of about 9 and about 19. So this means, well, so obviously there's a large uncertainty range because of there are large uncertainties because of the limitations of the data. But these are showing a significant increase in the risk of such an extreme hot summer in the present climate compared to the 1970s. And similarly, so this is looking at the winter spring precipitation. So here you don't see a clear shift in the sort of precipitation distributions, and similarly, there's not a significant change in the risk of such an event between the two periods. So both model sets show a decrease in the risk of an extreme dry winter spring period, but it's not a significant risk. And then looking at the summer precipitation, so again, you don't see a significant shift in the distributions, and again, you don't see a significant change in the risk of such an event. So the risk ratios are above 1, so that's indicating that the probability of the event has increased, but the results are not significant. So in terms of looking at the joint event probabilities, so looking at the combination of hot and dry summers, or hot summers and preceding dry winter spring periods, because we're looking at an extreme event, it's quite difficult to do this, because so these plots are kind of showing that there's no or very few years where more than one extreme is exceeded in the model data sets, because it, by definition, it's a very extreme event, and because we have a limited sample size. So I've used the method of bivariate copulars to generate joint distribution functions of pairs of variables. So I've used this to evaluate the joint risk of of pairs of these three factors. So so this is not very well presented in the table, but so the top table is showing the risk of the extreme dry winter spring period and an extreme hot summer occurring in the same year. And here, if you look at the risk ratio, you see that the models, both model sets are showing a significant increase in the chance of this combined event occurring. Looking at the extreme dry winter spring and extreme summer, the models are showing increase in the risk, so risk ratio is greater than 1, but these are not significant changes. And then the risk of an extreme hot and extreme dry summer has increased significantly. So you've got risk ratios significantly above 1. So just to summarize, so in this work, I've evaluated the change in the risk of the 1976 heatwave and drought events since the 1970s, and I've used an event attribution-based methodology. And so I found that the risk of a summer as hot as 1976 in the England and Wales region has increased significantly between the 1970s and the recent decade. And actually in the current climate, such a hot summer is not really extreme anymore. It's kind of, the return periods are now 6 to 8 years. So we do expect to have these kind of very hot summers quite relatively frequently. The changes in, well, there's no significant change in the risk of very dry winter, spring, or summer periods. But the change in the temperature is sort of dominating when we're looking at the combined risks. So the combined risk of an extreme dry winter, spring, followed by an extreme hot summer, and an extreme hot and extreme dry summer have increased significantly. And so an important point is that water resource systems need to be robust enough to cope with the impacts of more frequent occurrences of summers as hot as 1976 in combination with dry winter, spring, or summer seasons. So they shouldn't be making an assumption that the risk of this kind of joint event has not changed since it occurred. And finally, this work is now published in the Quarterly Journal of the Royal Met Soc. So the link is at the bottom of the slides. So thank you.